next talk is by me, and we'll be leading off a sequence about virtual object layer architecture and overview for my talk, and then a series of talks about connectors that implement different features and capabilities for HDF5 within the VOL framework. So I'll start off with that overview, and we can then proceed into more detailed descriptions of other VOL connectors directly. Here is this. Start presenting, and I do not want this slide. So, my name is Quincey Koziol. I'm with Lawrence Berkeley Lab, the NERSC supercomputing facility, and hopefully during my 20 minutes, let's try to cover this, right? High-level intro to what the virtual object layer in recent releases of HDF5 is, a description of what that architecture and drilling down to the implementation details, and very fast, creating your own VOL connector as a developer. So the virtual object layer, or the VOL, in HDF5 is a new abstraction layer within HDF5. It's a mechanism built into the library that redirects I/O operations, anything that stores data, into VOL connectors immediately, very close to the top level of an API routine. Immediately when the API routine is invoked, everything else, non-I/O stuff, goes into the library infrastructure. I'll show you some pictures about that. VOL connectors themselves are the mechanism to implement storage for those HDF5 data model objects, data sets, groups, files, attributes. And those connectors implement methods in an object-oriented sense on the objects. So here's the contrast here. Sometimes we've talked about virtual file drivers, also a pluggable way to store data, but virtual file drivers deal with byte offsets and very low-level POSIX-like infrastructure. And VOL connectors deal with objects and methods on them, so it's a much higher level of abstraction. They do perform very different functions within the library. I'll show you some pictures about the relationship for them, but they are very different things. You cannot substitute one for the other. So VOL connectors themselves, they can be transparently invoked from a dynamically loaded library at runtime. You don't have to modify your source code. You don't even have to rebuild your app binary. You just set an environment variable and go, and I'll show you that. So these VOL connectors, they can be stacked, and that allows you to implement many different kinds of connectors. We've kind of named them as pass-through connectors that are the ones that actually can be stacked, but they eventually have to resolve down to a terminal, a final connector. And terminal connectors, these are non-stackable. They have to be kind of the bottom layer, the final connector in your stack of VOL connectors. Pass-throughs are really, really useful for things like provenance tracking or logging, caching. We do some very fancy stuff to implement asynchronous I/O so that you can implement defer operations into the future and execute them in background threads. And speakers will talk about async I/O and caching both in follow-up talks. And terminal connectors are very nice ways to access data in some non-HDF5 way, typically. Some examples of that are this remote access, whether you're going to store data in the cloud or a non-HDF5 file format. This gives us access to existing ecosystems of legacy or current, depends on your perspective, right? Data that you may have. Petabytes of whatever can be accessed through the HDF5 API if you write a VOL connector that understands that file format, and then you introduce all those legacy files into the HDF5 ecosystem. And modern high-performance computing and other places are beginning to take seriously some of the object stores and the current technology development, such as Deos and cloud scenarios. So these object stores can be plugged into the HDF5 data model with a vol connector and then accessed in ways that aren't currently possible. You don't want to store a native HDF5 file in the cloud. It's a very poor choice. It's just a very big binary blob to the cloud. So this looks like, from very, very 20,000 foot level, all the operations on a container, a file, but more modern days, these are really just containers. They won't always be files. Get into the virtual object layer, that whole framework here on the left, and everything else, data type conversion, property lists, IDs, anything that doesn't store data. If it's runtime only, it goes over here into the library infrastructure part of the library. But if it touches a file, it can pass through one or more pass-through connectors. And I show some examples here again, and you can stack these guys, like I say, and then resolves eventually to something that stores the data. Could be memory, disk, object storage system in the cloud, wherever you want. Eventually it resolves to, yeah, your data goes somewhere with a terminal connector. Kind of zooming in on this, the framework that is implemented to handle all the virtual object layer things first passes through any vol connectors that are pass-throughs, resolves down into these terminal ones. And I want to show here that the VFDs, the virtual file drivers I mentioned earlier, those are part of, within the native connector for HDF5. So if you're working on a VFD, you're already within the native connector, and you won't be able to talk to a Deos thing without doing something very, very special, very unusual as a VFD. And likewise, the Deos plugin or the Adios BP plugin, any of the other vol connector themselves, they don't interact with the VFD layer at all. They're completely separate things. You could write a driver that was callable by a connector, but you're kind of really mixing up things. I wouldn't necessarily recommend that. It's possible, but that's typically the architecture that you're dealing with looks more like this. So I say, hey, the vol framework is an abstraction there within HDF5, and IO operations are redirected into the connector, and non-IO ones go into the library infrastructure. What's that look like as a programming perspective, right? So this is a very standard HDF5 skeleton we show lots of times in tutorials. Create a file or open it, create a data space, create the data set, do some IO, shut things down, right? Well, with the vol framework and the modern HDF5 libraries, most of these calls, the ones you'd expect, things on data sets, things on files, operations on those storable objects, are going to get redirected into the vol layer. And the other piece, data spaces in this example, are infrastructure calls, and those won't touch the vol interface at all. They won't even, they don't connect to it, they don't intersect with it. There's no way to write a vol connector that handles data space operations. It just isn't connected. So I'm kind of drilling down now into the details of things, right? So if the vol framework is this abstraction layer and it's redirecting IO operations into the connector, what's that look like in the code? So this is, if you checked out HDF5 today, basically you'd get code. I've kind of reformatted a little bit. I took out some argument checking so I could squeeze it on the screen, but this is the code for a dataset read call. And highlight a couple things here and then talk about the aspects of how this applies to the vol framework. This piece of code, the highlighted piece of code, resolves that ID that the user is dealing with, the dataset ID in this case, to a vol object, something that can be invoked or have methods invoked on it through the vol framework. And then once we have that object that we, picked up from the dataset ID, we actually call into the VL, the vol framework, and we say, hey, yeah, we got this vol object. I'd like to perform a dataset read call on this. Please go do that. Then, depending on the connector stack that you've set up internally, the virtual object layer framework, the code inside HDF5 library, will actually make callbacks, function calls, into, for example, pass-through asynchronous I/O connector that has an underlying native vol connector, or that dataset read could end up in the Deos vol connector, or be actually reading data that isn't in an HDF5 file. Maybe it's an Adios BP formatted file. Those happen internally. I won't show you all the gory details. There's many thousands of lines of code that make this all happen. But that's internal to HDF5, and you connect that up and build the connector in order to have that happen. The framework just invokes your methods, your function calls in your vol connector. So, as I say, the actual vol connector implementation defines these callbacks, and then either it terminates the call, it does whatever you asked it to do, dataset read, or it passes that operation through. It may log it or do some other operation as it's going by, but it invokes an API connector interface call to actually pass it on down to the next level below it for pass-through. So we're going to try it. I've set things up. I think we can switch my sharing to my whole screen, and I can run through these steps and it will work. We'll see. At least it's on my laptop. The cluster won't crash today. So if you want to go develop a vol connector development 101, subscribe to the vol mailing list, right? Email to subscribe so that you have access to a community of people doing similar things. You can ask questions. You know, I hang out there, the other vol developers hang out there. We can answer questions and ask and think about design work that might need to be done, problems that you've exposed. So first step, thing I would recommend, the easiest way to get into vol connector development, clone this external pass-through example vol connector. And external connectors are the ones that can be invoked using environment variables, right? And this one in particular is very, very simple. All it does is just pass through whatever the callbacks that HDF5 makes to the underlying vol connector. So this one, we're going to show an example of stacking it on top of the native connector. This is a great way to get started and have a working thing that you can build in like 10 easy steps that you can start modifying to your purposes for your own HDF5 vol connector, whatever you're trying to do. So going to this URL here, this is that Git repo. We've got a good README here that shows us what we want to do. And I've got a terminal connection. So I've already done this, so I'm just going to scroll through my history here, right? We clone the Git repo. Have to go change the makefile, right? HDF5 is installed on my system in a particular way, right? I have the advantage that I've already, sorry?
Should we be seeing something other than your browser here?
Nope, this is my terminal window, yeah?
That's not appearing, at least for me anyway.
Can other people see the terminal window?
Yeah,
I see. Mm-hmm.
Yeah, I see it.
I'll try rejoining, sorry.
Okay, that's fine, thanks. So I have the advantage of, I pushed the directory that I've got my installed HDF5 in here to the Git repo, but just modify the macros here in the makefile to whatever your system build looks like. Run make. It builds up the dynamic library that we'd like, this lib h5 pass-through vol.so, right? Then we've got to tell HDF5, hey, I'd like to use this vol connector, and it's located here, and here's how to load the dynamic library. So these environment variables need to be set. And I'm on a Mac, so I need to do that instead of this LD library path piece. But again, I've already kind of preloaded that into my environment. So plug in path first. I'll just do it in the order we got here. It doesn't matter much. Library, great, okay. So now in theory, HDF, I've got the library built, I've got this nice pass-through built. The library understands or should understand where everything is located. I've got a sample HDF5 file here in this directory, comes with the Git repo, and I'm gonna run pre-built HDF5 LS on this sample example file. So this is the H5LS that I've already installed in my system, just there. It's totally unaware of this VOL connector that we just built, right? And we're going to point H5LS at the sample HDF5 file, and it should work correctly and give us some output. By default, the debugging output is on for the pass-through connector here, and you'll see some of that as we get H5LS output. So super easy to get in and clone a copy of a VOL connector that works. Like I say, 10 easy steps. And you can have a VOL connector that's built on your system, works with your copy of HDF5, works with applications that are not even aware of your VOL connector. You can set the environment variables and just have them access your data. Hopefully, people will be able to use that as a mechanism for getting in and starting their development. It's very easy. If you have questions, you can ask on the VOL connection, or I'm sorry, the VOL development mailing list. We're gonna, like to thank everybody who's, both funded this and helped design and implemented it at many different locations. Argonne, Berkeley, the HDF group, were funded by the DOE Exascale project. And any questions? No questions. All right.
It is easy, so it's crystal clear. Thank you, Quincey.
It worked perfectly. It only took me an hour to get it perfectly set up in my terminal, but it does work just out of the box. There's nothing special I did locally, really.
So there's one question in the chat window.
Ah, sure.
How does H5LS know to use the VOL?
Right, it's the environment variables. Those environment variables have specific names that the HDF5 library, is predefined to go look for things named with those particular three. Well, the dynamic library path isn't part of HDF5. That's part of the OS. But the HDF5 pieces of that environment variable settings are explicitly looked up within modern versions of HDF5.
Can that VOL setting also be done by the application?
Yeah,
or does it have to be? Okay.
Yeah.
So so sometimes we use MPIIO to get, all of our processors going down to a single file, but sometimes people write like subsets of the file, so there's not much data coming out and the MPIIO is just a big overhead. Could you write a VOL that would, our application would recognize we're not going to put out much data, so instead of calling MPIIO with each process, just the VOL would pull all the data over to processor 0 and write to a serial file? Is that something a VOL could do, or?
I think probably could be done. Sounds a little bit like a pass-through connector that wants to layer on top of the native connector. Here, I'll share this slide that I had earlier. Seems like you could write a pass-through that either detected this dynamically or, was custom built and explicitly designed to do that all the time. And then invoked, the native connector underneath it to perform all the IO, maybe even just with the POSIX connector and not the MPIO connector, right, from rank 0.
Okay, thanks.
Sure. Any other questions? Okay, that's about all the time we've got.